And so we have come to the last presentation today that will provide us a better understanding on simulation-based spin pack design. Let me welcome Christian Leithäuser, Senior Scientist at Fraunhofer Institute, Germany.
Thank you very much and welcome. So I'm working for the Fraunhofer Institute for Industrial Mathematics, and what we are doing is we simulate and model and optimize industrial processes, and our group is specialized on fiber processes. Today I want to talk about spin pack design, how we can help engineers in designing spin packs in combination with CFD simulations. So yeah, our goal is always to improve designs and do this together with the help of the engineers, of course, or help the engineers improve their spin pack designs. So what we do is, if there's an existing spin pack, we can do flow simulations for the spin pack and then analyze the flow properties like residence time, like pressure, and then if there are problems, for example, you're using a new polymer, sensitive polymer, spin pack is suddenly not working as planned anymore, and for example, you suspect that there are some problems with residence time, for example, or you get problems with pressure, then we can do CFD simulations of the spin pack and then use these to optimize the design. And yeah, I want to walk you through the process. So how can we set up such simulations, and yeah, what can be done with the data and the analysis. So let's begin. Just for illustration here, basic setup for a spin pack. So we usually have some inlet tube where the polymer coming from the extruder and the spin pump enters the spin pack. Then we have typically some kind of cavity where polymer is distributed onto some filter devices. We have a breaker plate which somehow supports the filter, and then we often have a second cavity before finally there's a spinneret plate with small nozzles where finally the fibers are formed. So yeah, all the spin packs, of course, are looking different, but we usually start with drawings or CAD data, which customers provide us with, and then build a computer model from this. So for today, I will begin with yeah, short introduction. What do we need for setting up the model? Show some simulation results for this sample spin pack, just for illustration. Walk you through some steps of analysis, and then show some results on our shape optimization techniques, where we can improve certain aspects of the design in an automated fashion. So let's begin with modeling. So what do we need in order to simulate a spin pack? First, of course, the geometry. We use this to build a computer model. And then rheology of the polymer always plays an important role. Especially, we need data on viscosity and on density. Here are just some literature values for polypropylene, but of course, whatever polymer you're using, either the polymer manufacturer can provide measurements on the polymer, or they can be done in a lab, and this then enters the simulation. So here just viscosity curves where you can see the shear thinning effects and also the temperature dependence of the viscosity. This enters the simulation. Then second step, which has to be considered, are the filters. Filters usually generate a pressure drop. So when having a look at the flow of the spin pack, this pressure drop is quite important, and we have to include it in our model. So what we usually do in order to tackle the filter is a multi-scale approach. So the filter, of course, has many small cells and we cannot resolve all of them in a whole simulation. So in order to get the correct properties of the filter, especially the correct pressure drops, we simulate individual cells of this filter. So often you have mesh filters, several layers of those, and we simulate single cells of these meshes in order to compute pressure drops of the individual layers, and then we can, in the easiest way, add them up to a complete pressure drop through the whole filter layers. Use this to identify parameters for our filter model, like permeability and porosity, and then feed this back into the whole simulation in order to get then correct pressure drops for this one. Second thing is capillaries. If you only have 100 or something, several hundred capillaries in your spin pack, in your spinneret, then usually you can simulate them as is. So just resolve the geometry, get all the effects. If we are talking about several thousands or 10,000s of capillaries, then we also can do something similar to the filters, do a multi-scale approach in order to capture the important properties of the capillaries, like the pressure drop, and then also use this to identify parameters for permeability and porosity, and feed this also back into the full model. Then we can simulate the spin pack. Flow simulations are done with commercial software, so we can usually use ANSYS Fluent in order to do this. Here you can see some illustration of the flow path of polymer going through such a spin pack, or especially through this sample spin pack, which I use here for illustration. The flow velocity is depicted by color. Very slow velocities are blue, and higher velocities go up to red. And if we have another look at the cut through this spin pack, we can already see that we have some stagnation zones, like here in the blue regions, where we have very low velocities. And these may be zones where stagnation can take place. We want to do something against this. Before we do this, we have a look also at the pressure distribution. So you can see that we have main pressure drops here where the filter is sitting, and down here, of course, the main pressure drop is occurring in the capillaries. Then having a look at an analysis, so we have now just some colored pictures, but we also want to do some statistical analysis on, for example, the residence time. What we can do there is we take a representative number of flow paths through the spin pack. Of course, every flow path has different residence time, and we want to look at the spread of this. So typically we use all the flow paths which somehow end in the center of the capillaries, and then do some statistics on this. And here we can now see the spread of the residence time for this specific spin pack. The fastest path or polymer particles need just about 20 seconds, and it then goes up to 180 seconds. So here you have quite a large spread, and then also the analysis shows you in what part these high residence times are spent, and you can see that this is mainly in the cavity 1, shown here, where the polymer is distributed from the inflow tube onto the filters. So second thing, we can have a look at the pressure again, and also see where the main pressure drops are happening. So mainly in the breaker plate, at the top of the breaker plate, where the filter is sitting, and on the capillaries. So we have seen, okay, we now have, may have some problem in residence time. Of course, depending on your spin pack, the analysis will also identify different problems. So especially if we are talking about bicomponent spin packs with very small channels, then you would probably get a totally different picture, because then suddenly pressure plays an important role, and you will see the regions or the small channels where the large pressure drops are generated. But just for this showcase, we are now have a look at residence time, and we want to reduce the residence time of this cavity. What we have done is use shape optimization approaches to design optimal cavities. I mean, you can clearly see that this rectangular cavity is, of course, not optimal. You have quite a lot of stagnation in the corners. So our approach here is that every stagnation zone here in the corners somehow is connected to the wall shear stress at the wall, because if you have a corner, flows very slow, so you have very low friction on the walls, and the wall shear stress is very low. So we use the wall shear stress as an indicator to optimize the spin pack, and then use some optimization approach to design or redesign the spin pack cavity. Basically, it works like this. So we have some initial geometry. We solve the flow equations, so compute a velocity and pressure, and from this we can evaluate the wall shear stress. And then we have some optimization cycle, which is able to rise this wall shear stress level up to a certain threshold. And then we know that if we are able to get the wall shear stress up, then also these stagnation zones close to the wall vanish, and we get a better residence time profile. And then you get something like this here, or making it a little bit bigger, shapes like this, which have been optimized with respect to wall shear stress. And we put this together with the original spin pack and switch the cavity, get something like this. So this was a setting which was designed for some medium level of wall shear stress. And here we have some higher level of target wall shear stress, just a second variation, which we again use to optimize, and then get two optimized designs. Now again, comparing the residence time, we have here, residence time in blue was the original setting, then the first optimized version with the medium target wall shear stress, and one with higher target wall shear stress. And you can see that it was possible to greatly reduce the residence time in cavity 1, and therefore also reduce the total residence time, and also, of course, the spread of residence time in the spin pack. And doing this with the wall shear stress criterion in an optimal way, such that the pressure is not influenced too much. We can check this here. Again, having a look at the flow velocity in the spin pack. So at the top, you can see these large regions with very slow flow velocities, and we were now able to reduce this to a very, very low layer at the wall. And in here, get some optimal distribution of the flow velocities, and therefore reduce the stagnation zones where degradation of sensitive polymers may take place. Having a look at the pressure, we can see that basically the pressure has not changed much, because the main contributions are still in the filter and in the capillaries, and in the first cavity, pressure was not a problem before, and it's still not a problem yet now. So for the first approach, we have used the the wall shear stress as an optimality criterion. Now, of course, the question is, can we directly use the residence time itself? And we've also been working on using the residence time as an optimization criterion, which is now recent work from us. And the optimization cycle is basically the same, with just one difference. You again solve the flow equation, and then you need to solve a second equation which measures the residence time. So basically you trace particles through the spin pack and then use this to compute the residence time. The advantage of wall shear stress as a criterion was that you could directly figure this out or compute this from the flow velocity. Now you need another solving step in order to compute the residence time. From this you get the residence time and then can do again an optimization loop and get some improved residence time distributions. Here a little bigger. So that was the end of my talk. So we at Fraunhofer Institute for Industrial Mathematics, this is one thing we are doing, and besides that, we are doing quite a lot of modeling, simulation, and optimization for the fiber industry. So also models for fiber dynamics, where we look at what happens with the fibers after the spin pack, how do they form nonwovens, and things like that. So our stand is right outside the store on the left side, first stand there. So thank you very much for listening.
And any questions, our speaker?
Do you really implement the simulation in the real?
Sorry?
Do you have implemented your simulation one in the? How about the
We are using this. So I mean, the pictures you saw here are just a demo case. I mean, we are not showing any real spin pack designs from our customers, but we have had many projects where we use this directly with customers in consultant work. So this is always also the goal of Fraunhofer to not only develop the methods. So we do some base research, of course, to develop methods, but then we always use these in consulting projects. And this is what we are very actively doing with the spin back design. So everything you saw today is, of course, is demo material to just showcase what's possible. But yeah, we are applying these methods, yes.
Start about the bicomponent system?
We have also worked on bicomponent systems, yes.
And how about it?
I mean, the setting is, of course, totally different, because now residence time is not so important, but pressure suddenly becomes much more important, because you somehow have to get everything into the nozzles, and then you have these microchannels. And if one of them is a little bit too small, you will directly see this in the pressures going up. And so their simulations really help to identify which channels are too small, which are good, and how can you reduce the pressure of such a system.
What kind of bicomponent system you practice now?
I cannot comment on this because it's confidential.
More questions?
Thank you for this very interesting speech. This was regarding the spin pack, but of course spinning is also something a little bit more, also the melt piping, pressure, temperature, quench. So this also, you work on these issues, and maybe that you can later also combine the complete. Is this some of your goals, or?
Yes, I mean, all these problems are of course different, and we can combine certain models, so we can have temperature, include temperature measurements, or temperature into the models if this plays a role. We also have, so if it's a spin pack or some other device, or if you're also interested in the flow from the extruder to the spin pack, or what happens in the spin pump, so this can all be included in the models. So basically, yeah, we have the tools ready, and then we can do consulting projects with these to identify, yeah, certain problems, yeah.
Okay, thank you.